Hi, ladies. This is my presentation on carbidopa, the use of X-ray crystallography, and as well as using the program Chimera to show you where the carbidopa bonds within the molecule. So in order to understand what carbidopa is, we need to understand what it treats. Basically what it is Parkinson's disease, which is a progressive nervous system disorder that manifests itself as movement issues. So the neurons in the brain gradually break down or die. These neurons produce the chemical messenger dopamine. And when these levels decrease, it causes the abnormal brain activity, leading to impaired movement. So for example, you'll see patients with Parkinson's that kind of shuffle their feet when they walk. They don't swing their arms back and forth. So you'll see bradykinesia, which is the slowing of everything. They talk slow. It takes them a really long time to put their shoes on or get dressed or use the restroom, etc. Speech issues such as slurring. They're very monotone, so there's no inflection within their voice, and they're very quiet when they speak. The other big telltale sign of Parkinson's is tremor, so you notice them shaking a lot. Their head will bobble, their fingers will move. It's just an all-over progressive movement. They'll have balance and postural issues. So, for example, my dad has Parkinson's. So not only does he tremor, but he also kind of hunches over when he walks. He falls very easily, so his balance is not where it should be. And then eventually you end up with the loss of automatic movement, such as blinking, facial expressions, eating becomes an issue, swallowing becomes an issue, and that seems to be in more of the advanced state. So essentially there's no cure at this point, but these medications that we'll talk about will significantly improve symptoms if taken. So carbidopa is what we were asked to talk about. It's also known as under the trade name as Ladocin. It's used to treat the symptoms of Parkinson's disease, specifically the tremors and the rigidity of the muscles. It can also be used to treat Parkinson-type symptoms, which is caused by the side effects of certain medications, poisonous gases, as well as some minerals that become ingested. It's commonly used in conjunction with levodopa, which is the other Parkinson medication that we're going to talk about to kind of bring all of this together for better understanding. Carbidopa is also an aromatic L-amino acid decarboxylase inhibitor. So this is an enzyme, it inhibits this enzyme. So this is the structure of carbidopa. So carbidopa and levodopa kind of work in conjunction. The levodopa works within the central nervous system by being converted into the dopamine once it reaches the blood-brain barrier. So levodopa is the precursor for dopamine, which is converted into dopamine by the L-dopa decarboxylase, or DCC, or DDC for short. So basically the DDC is the activation that leads to the production of the dopamine and the serotonin that your body needs for movement. Carbidopa works by preventing this levodopa from being broken down before it reaches the blood-brain barrier. So in conjunction, the carbidopa helps the levodopa to get into the brain, so it can be broken down to make the dopamine that is necessary for the neurons to be sharing the messages between your nerve cells in order for the movement to work. So dopamine, like it says, is a neurotransmitter that your nervous system uses to send messages between nerve cells. And so basically what happens in Parkinson's is the dopamine dies or fails to be made, and then the messages between nerve signals ends up not being relayed, which ends up with the rigidity, the tremors, the postural balance issues that we talked about. Carbidopa can be administered both orally, inhaled, or infused, depending upon basically where the patient is within their disease process. So this is just a quick little schematic. So essentially the levodopa is what is necessary to make more of the dopamine in the patient's brain so that the neurotransmitter can work. But carbidopa is given in addition to it, so it breaks down this DCC so the dopamine isn't made outside of the blood-brain barrier, which is this right here. So once levodopa gets through this blood-brain barrier, you can kind of follow and see what happens. Then the dopamine then synapses out and does what it needs to do for the neurotransmitter, because here's the other nerve. So that's a little bit about that process. The next thing we needed to talk about was X-ray crystallography. And so we kind of talked about this already in our discussion, but X-ray crystallography is used to obtain the three-dimensional structure of a particular protein by sending X-rays through the crystal. And so the X-rays go through and it diffracts, and then what it does is goes through an electronic detector, which kind of shows where the X-rays are being diffracted from out of the crystal. The crystal is then rotated by a computer, which is used to obtain specific orientation set forth by the researcher. So basically, the researcher will put in like coordinates, kind of like a GPS system, I guess, and it kind of tells the computer how to rotate the crystal in order to get the necessary information. And then the intensity of each of these diffracted rays is entered into the computer, where then a series of math calculations are done from all of the positions of the sample, and it kind of will project, well, it will project you a 3D image, which we'll see in the next slide. And this is measured, the distance is measured within X-ray crystallography is measured between atoms in angstroms. So this is kind of a very dumbed down version, I guess, of how it works. The sample needs to be in a crystallized form. Then the X-rays are shot through this crystal, which makes this diffraction pattern. These diffraction points are then made into an electron density map. And then this spits out your final 3D structure of your protein. Now, this Carbidopa chimera thing, I'm a little not 100% positive about, so bear with me. But so by putting in Carbidopa into our chimera program, I kind of took away some of the side view so you could see more internally. The purple right here is the Carbidopa, and it's binding right here to this green outlined molecule, and this is called PLP. And so the Carbidopa binds to the DDC by a hydrazone linkage with PLP, and so this is kind of where it all bonds together. So I don't know, I hope that answered the question. I wasn't completely 100% positive, but you can kind of see where the Carbidopa then binds. And this is the inhibitor. So then this inhibitor will, or the inhibitor stops the breakdown of the levodopa before it hits the brain barrier, the blood-brain barrier. So I hope I didn't confuse you more. If you've got questions, let me know. Hope this was helpful. Thanks.